Right, in this video, we're going to attempt to conceptually develop the general case, or for calculating the potential difference in the general case. And what that basically means is we're not dealing with point charges or those conceptual examples like maybe an infinite plane or something like that, what the potential difference is between 2 points. So this is definitely going to involve some calculus, but the goal here is basically to do a proof of our equation for potential difference so that you understand where it comes from and that it's basically an energy perspective, like I've been saying, and hopefully it helps you. So my goal is to help you develop a clear understanding of the underlying principles for potential difference. And so we're going to start by writing the work is equal to the integral from a to b of f dot ds. Now, the reason it's a ds is because we're going to sum all the way along a line. So it could be a three-dimensional path. So this is going to be a line integral. The work done by the electric force is equal to the integral from a to b of the electric force Fe dot ds. And remember that this is just the electric force. And so in our next step, for the electric force, we're going to substitute an expression for that. So the work done by the electric force is equal to the integral from a to b of, now remember that F electric we could write as Q times E. And this F equals QE came from the definition of the electric field, which is F over Q. So that hopefully gives you a little perspective for what I'm going to write next, which is F is just equal to Q times the external electric field relative to Q dot ds. Now, for our purposes in problem solving, this E, this may be a constant field or variable field. All right, so what we're going to do now, Q being the test charge is a constant, so we can take that out of our integration and we're going to actually move it to the other side. And so we're going to get the work done by the electric force divided by Q is equal to the integral from a to b of E dot ds. All right, now we know that there's a relationship which exists between work and potential energy. So work is equal to the negative of the change in potential energy. And so instead of writing this as work, I'm now going to write it as potential energy. So we get delta UE over Q minus delta UE over Q is equal to the integral from a to b of E dot ds. We can rewrite this negative delta UE over Q using our definition for potential. So delta V was defined as delta U over Q. And so because this is negative, we get a negative delta V is equal to the integral from a to b of E dot ds. And then finally, we want to get this negative sign on the other side so that we get our potential difference is equal to minus the integral from a to b of E dot ds. And this is our general equation to determine the potential difference for any electric field. Now this is going to be really important because we're going to learn later that, when we want to calculate the potential difference, this is the reason why we did Gauss's law, right? And it's not just Gauss's law. We can also do this for the continuous charge distributions where we were just looking at a rod that was a short rod or something like that, or a disk. And so, but this is why we study Gauss's law, because we need to come up with a field model, a spatial field model for the electric field, so that we can calculate the potential difference.